you're okay with say yes.
All right, we're gonna go ahead and get started. Yep. Thank you everyone for coming again. I'm really excited about. I was excited about neurophysiology last time, but I think neuroprosthetics will be fun. I really like GIFs. You'll see that in here. Like more than half of this presentation is just GIFs because I'm just going to kind of talk about some different technologies and show you guys some cool stuff. So yeah, again, as always, thank you for coming, and feel free to ask questions as we go through as well. Although I'm guessing this one might wrap up a little bit earlier than the other ones, so there might be some time at the end as well. So this time we're working from a different book. I have it over there if you're interested to take a look, but this is Brain-Computer Interfacing: An Introduction by Rakesh P.N. Rao. Really, really great overview if you're interested in neurotech at all, whether it's invasive or non-invasive. Highly recommend starting here. So we're going to talk about some methods of how you actually collect and use brain signals to do certain tasks. And then once we have kind of gone through that and gone through all the different methodologies, we'll then jump into some applications. And again, I'll just show you GIFs on GIFs on GIFs on GIFs of different things that people have done with neurotechnology and brain-computer interfaces, and then just kind of do a quick explainer as to what technologies they're using to make that happen. And hopefully you'll all be a little bit familiar with that because we will have gone over some of those techniques above. All right, so how do these devices actually work? What are the methods that underlie this technology? So there are three components that we can kind of break down conceptually how to make these devices work. And so the first one is collect. Of course, you have to pull in the data. These deals with the devices that you're using. Encode, which is that processing part, also filtering, taking out noise, because these are really sensitive signals. And then finally, the deploy part, which is what are you actually doing with it? What do we want these signals to mean? What are we looking for? And then what are you controlling in the end? So how do we collect and influence these brain signals? This part might be a little bit of a review just for you being in the club, but these are just some of the quick overview of some of the technologies that can be used. So you have devices that are completely invasive, like microelectrode arrays, which are up here on the top. So this is underneath the skull, and this is actually penetrating brain tissue. So these are tiny little electrodes. And then you even have some called DBS, deep brain stimulation, which I'm sure John will talk about a little bit. Is that next week that your talk is?
Monday the 14th. Yeah.
On Monday the 14th, John will tell you all a little bit about deep brain stimulation, some other technology. But these are invasive, is actually penetrating brain tissue. You then have semi-invasive like this. This is an ECOG or electrocorticography array sitting on top of the brain but not penetrating it. So a little bit less signal quality, but a little bit safer. And then you have technologies like EEG, which is the main thing that we talk about, which sits in the non-invasive side outside of the skull. So electroencephalography, or EEG, is the main technology that we use, well, that and EMG. And it's the most common BCI interface because it's really, really cheap. You can buy these devices for a couple $100, like the BCI ones that we use. And it's been used for a really long time. And so this is collecting electromagnetic waves, electricity that is picked up across the scalp. And you're actually looking at synchronicity. So neurons firing together gives you these big waves, or neurons firing in different directions at different times gives you a smaller wave. And you're looking at the differences of those. And that's kind of the primary thing that you're doing with EEG. You can get a lot of information from that, which we'll go through for a little bit. It has high temporal resolution, which means that it's really fast. So it's electricity. So pretty much as soon as a new thing is happening in your brain, you see that. But it has low spatial resolution, which means that it's not really specific. So you've probably all seen this, but this is from the OpenBCI GUI. This just shows what raw brainwave data looks like. They're changing the scaling, but you can see it's really, really messy. And from us just looking at it, there's not a lot that we can interpret from that. Electromyography, EMG, is muscle sensing. So electrical signals that move through your muscles can be picked up in a pretty clear spike. So you can see some electrodes are stuck to this person's arm here. So that's one way that we can get signals. This is really easy and really cheap as well. Here's a video of Colin controlling a prosthetic arm using a jaw clench, so using his muscles on his jaw. Again, I'm sure some of this is review. This might be a new technology that you haven't heard of. This is called magnetoencephalography. A lot of these crazy names, or MEG. And so these are very, very expensive devices. This device up here is one of the cheaper ones at $100,000. It just came out last year. But what this is doing is measuring magnetic fields as opposed to electricity. And so it can penetrate a little bit deeper. The signals are a little bit clearer than EEG, but still it's quite fast. Of course, the limitations are that you need a magnetically shielded room, and they're quite expensive. But this is, a lot of neurotechnologists think that this is kind of the next evolution onto EEG. For the last of these, I believe, of the non-invasive brain sensing ones, we have functional near-infrared spectroscopy. And what this is doing is it's measuring blood flow, where blood is flowing in your brain, to determine cognition. So the idea is if a part of your brain uses up more energy, it's going to need more blood to go to it, and more energy means that it's more active. And so these devices, you can see, kind of look like EEG. They sit on the outside, and you have a lot of these sensors. And they can get quite small and cheap, too. I know a company that's working on making a $200 one that sits on your glasses. It kind of depends on the application, but this is interesting as well. Not as fast as EEG, but it gives you more depth. Electrocorticography, which I talked about before. This is, sorry, warning. I should have warned you ahead of time that there are going to be some gross images. I'm very used to just seeing this stuff casually now. But this is an electrode array that is placed on top of the brain. You can see we're covering a pretty decent amount of area there. So it's placed right under the brain, or right on the brain under the skull, really fast like EEG, and kind of in the middle between invasive and non-invasive interfaces. And then this is a close-up of what those microelectrode arrays look like. So you can see there are a lot of these little jagged spikes. On this one, there are 100 little spikes there. And so you implant that in an area of interest like the motor cortex, and then you can use that to control prosthetic arms, or you can use this for stimulation as well in the peripheral nervous system to give you sensation, or in the central nervous system as well. And it's really quite varied in its applicability. One of the problems with this is that you can see that's a rigid structure. Your brain moves. Your brain is not a rigid structure in your head, and so that creates a little bit of scarring. Scientists working with this right now have kind of said, well, this is for people with motor impairments that are kind of in their wheelchair and they're not really moving anyway, but that's kind of an unsatisfying answer. And so there are companies like Neuralink, you may have heard of Elon Musk's company, that are looking to address this by using methods that are more flexible. So this here, these are all individual electrodes on threads, and it's kind of hard to see, but this is brain tissue here, or mock brain tissue. And they put these threads in individually, and then all of those threads kind of connect back to a module that's implanted in the skull. It's like a mock piece of skull, so it kind of sits in your skull like that. And then that allows your brain to move independent of your skull, which should make it safer. Although Neuralink has had a lot of ethical violations that have come up in the last couple weeks. So, and it seems like these devices are maybe causing more damage than they're worth, but it's an interesting idea as of right now. Deep brain stimulation, John, are you going to talk about that in your talk?
I would say go ahead now.
Okay.
I'll probably hit more non-invasive stuff.
Okay. Yeah, so there are stimulation technologies that go deeper into the brain. So you can see there's this electrode that actually comes down into the very central areas. And this is an FDA-approved technology that's been implanted in more than 200,000 people worldwide. And it's really useful for things like chronic anxiety and depression, bipolar disorder, some research into ADHD, although that's usually not detrimental enough to warrant getting a brain implant, but it's also useful for addiction and obesity. So there are a lot of these functions that are that DBS is looking at, also like Parkinson's and movement disorders. So it's really interesting. Again, kind of scary seeing a giant spike go into the brain. They do these surgeries when you're awake to make sure that they're not damaging anything important. You don't have sensory receptors in your brain, so you don't feel it. But kind of crazy looking at some of those surgeries. TMS, you'll probably talk about though?
Yeah.
Okay. So TMS is a technology that uses electromagnetic fields to stimulate the brain, which you can use for anxiety, depression, chronic migraine treatment, as well as some cognitive enhancement as well. And spinal cord stimulation, this is the last last one of the technologies that I'm going to go through. But spinal cord stimulation is used for things like if you have urinary issues, it can help with that. It can also help with chronic pain. That's a big one as well. That's caused from neurons failing in the spine. All right, so how do we make sense of all this brain data? So I just showed you a bunch of different ways that we can collect data, but as you saw with the EEG GUI that was being shown up, that raw data is really, really hard to interpret. And us just looking at it as humans, there's not a lot that we can glean from it other than you can see the waves get a little bit bigger, a little bit smaller, and make some inferences based on that. So the first type of brain-computer interface that we have, the first like general methodology, is called asynchronous BCIs. And these are brain-computer interfaces that you're using conscious control over. So I'm thinking that I want to do a specific action, and it actually does it. I'm doing this consciously. One interesting thing that some of you might run into if you start using EEG is that depending on the population, depending on the study, there's about 15 to 30% illiteracy with brain-computer interfaces. And that just means that regardless of intelligence, regardless of other factors that we can figure out, there are some people that just can't do this, and we don't know why. There are just as much training, you can do training on training on training. Sometimes these asynchronous BCIs just don't work for some people. But this stuff is pretty cool nonetheless. So motor imagery, we've talked about a little bit in the human subject research, but this is imagined movement. So I'm imagining either myself moving forward, backward, left or right, moving an arm, just imagining some sort of movement, and then trying to use that to control different devices. And you can do this with invasive or non-invasive devices. The next one is called population coding. And so this is for invasive implants, and this is how they do neuroprosthetics. So as you'll see a little bit later, there are devices that are really, really accurate and work as if it's your own hand. And so what they do is they put one of those microelectrode arrays, those spike arrays, into your motor cortex, and they start listening around to different neurons. And as I talked about in that first talk, the neurons in your motor cortex aren't actually recruiting individual muscles and telling these muscles to contract. They're just telling your spinal cord, I want to move my arm over here, or I want to move my arm over there. And how we do that is you get a bunch of different neurons in an area that are, do I have? Yeah, I do have XMOs. A bunch of different neurons in a given area. And so we'll say this is one neuron, this is another, this is another. And each of these neurons prefer different directions. So this guy likes that way, this one likes that way, this way, that way, and this way, etc. And so you have thousands, if not millions, depending on what you're looking at, neurons that are under this area. And if you want to move your arm up this way, then neurons that like that way are going to fire, and neurons that like this way are not going to fire. And if you're going like this way, vice versa. And so what neuroscientists do is they put in a little chip, and then they tell you, imagine moving your arm this way. They do that a lot, and then they sort of figure out where these neurons are. And so this is a representation of what that looks like when they organize it. So you can see the person in this little animation wants to move up or forward, and you have neurons that respond to that. A lot of firing for the ones that go up, some in these other directions here, a little bit sideways, and then pretty much nothing on this other side. And so basically what neuroscientists do is they count up how many times neurons are firing in all of these given areas based on what they know about which direction they prefer, and then they just draw a vector that averages out the direction. So this is a little bit of a simpler animation, but here it gets a little bit more complicated. So what they were doing in this for training is they just had a monkey moving a joystick around, and when he moves his joystick to the right spot, then he gets a treat. And they were just recording in his brain what's going on so that they could then use this for a BCI afterwards. And so you see that the preferred direction is to the left here in this way. And you see that all the neurons that have a preference for that direction are firing a lot more than the ones that have a preference here. So all of these little things, I know it's pretty blurry, but all of these little dashes, that's one time that neuron fires. And so we're recording from, it looks like, 5 neurons that respond to each of these directions. And you can see when it wants to go to the left, a lot of activity here, a little bit less here, but still a decent amount, less, and then pretty much no activity. And so they can basically use that from recording from lots of different areas to control a prosthetic arm. Then, of course, there's just machine learning magic that a lot of you would probably know about better than I do. But these are two examples where someone was able to use a neuroprosthetic to type. So for this one, the person was just imagining, so this was at the Howard Hughes Medical Institute, if you're interested in looking this up. This person was just imagining themselves writing letters, just writing letters like as if it were with a pencil. And they were able to achieve about 90 characters per minute, which is crazy, of just imagining themselves writing letters. And so basically they would just say, write H, write H, write H over and over again, look for those signals using machine learning, and then look for that case where all of that brain activity matched what they had done from those training sets. Similarly, down here, this was from University of California, San Francisco last summer. And what they did is they said, all right, we want to record words directly from the person's brain when they're thinking about them. And so they took a set of 50 words and trained them trained the algorithm to look at what their brain activity was doing during those 50 words, and then were able to reproduce sentences and words just from thought. So entire words just from thought, as opposed to spelling out individual things. And granted, it was from a set of 50 words, but that's a really, really impressive starting point. And the person who was using it was completely nonverbal because of paralysis. So very, very interesting and promising results there. All right, so now we have the synchronous BCIs. So this is kind of on the other spectrum. These are responses in the brain that you cannot control. So these are just naturally occurring phenomena that neurotechnologists can use to control a device. I do want to give you a little bit of a seizure warning because there will be flashing lights. So if anybody needs to be aware of that, just go ahead and close your eyes, and I'll try to let you know when they're coming up. So one of them, and I put this one first because it's kind of in the middle of asynchronous and synchronous, is focus modulation. There have been a lot of games and little toys that come out that are related to this. And this is just you're trying to focus on an object, you're trying to make like this little, the little X-Wing fighter, like I think Yoda does, come out of the bog and whatever, so come up and fly, and doing that based on focusing on it. And focusing is really abstract, what I kind of mean by that, but what it ends up looking like is changing your brainwaves, so making them more alert. And humans are actually able to focus on a task and learn to modulate their own brainwaves. So it's kind of in between asynchronous and synchronous. These are those brainwaves that I was talking about. So these are fairly arbitrary lines that neuroscientists have drawn, but it helps us kind of understand what we're looking at in the brain. So these up here, so it's measured by frequency. These up here indicate a wakefulness and attention. Kind of the higher you go up in frequency, the more alert and attentive someone is. These are down in the deeper phases of sleep, and so this is traditionally associated with sleep. This is maybe relaxed, maybe asleep. And then when you're asleep, though, you might see activity like this in the beta range during REM. But other than that, usually you've got these big swoops. Okay, so other types of synchronous BCIs, we have event-related potentials. And so this happens when any event going on either in your brain or in the external world happens, you get this very clear signal that kind of looks like this. Now it can be stretched out, it can be compressed, but generally you have this positive peak here, and for whatever reason neuroscientists like to make things confusing, so the negative is up here and the positive is down here. But you have this positive peak, then a negative peak, followed by a positive peak, goes down a little bit, and then a larger positive peak. And so this is sort of what the ERP response looks like. And that could be like if you touch your finger on something, or if you see a new visual stimulus, or if you have a thought like you're making a decision, or you hear something that's interesting to you, your brain has this response. And then you can kind of separate these out into different types of signals, but that's all separated out from this, and then start to do different things with it. So this is really commonly used for keyboard control. For the BCI guys, Colin and I just made a Tinder swiper based off of this because this P300 signal is related to interest in an area of the brain that does like decision making and like an arousal. And so we use that to swipe right or left on Tinder based on the size of this P300. So you take a baseline, and whether it's higher or lower, you make a swipe. So you can do little things like that. Here's an example of how you can tell, how they're able to tell a certain area in the temporal lobe. So in these areas here, was able to actually detect someone's face. So we can see that when it's a scrambled face, car, scrambled cars, so just images that aren't faces, you have these up here. So you have this response, but then, and they're all kind of in the same range. But then when you showed this area faces, at about 170 milliseconds, there was this negative deflection that was a lot larger. And then subsequently in the positive direction, it was shorter, showing that this area is responsive to faces in a way that other areas were not, and it's selecting for that. So that's kind of one way that you can use it. I talked about that P300 signal. So this is using that same response. This is a P300 speller. And so basically, if you wanted to type the letter N, you would look at that letter, and you notice that you have flashing lines going in the vertical direction and the horizontal direction. And basically, every time this flashes, your brain gets excited. It's like, oh, that's my letter. Something happened to it. And you see this little P300 signal appear. So the computer kind of knows, okay, it's flashed this many times when I was in this direction and this many times when it was in that direction. And then it can calculate what letter you're looking at based on those overlapping signals. Here's another example of using P300, but this time to control a device. So again, you look at, they're highlighting different things, but you look at the right if you want to do that. Every time they flash over here, the computer is able to see that, pick that up, and then you can make something go over to the right. Here's just that P300 signal again, kind of what I was explaining. So when she's looking at this O, which is faint, you can't really see it here on the projector, but imagine that all these letters are all the way across and there's an O there. When it's not lit up, you see her brainwaves there's not really a whole lot going on, not that exciting. But then when the O lights up, you get this peak. And so when they overlap again, you kind of add up where those peaks are and can figure out what they're looking at. So just a couple other ones. The N100 signal, so this happens pretty immediately. This occurs when something is unexpected. So if there's a really loud noise, you can kind of detect that from this N100 signal. So that's kind of interesting. But I like this one a little bit more. This one occurs when something doesn't make sense. So if I read to you the sentence, I take coffee with cream and dog, your brain goes dog, that doesn't make sense. And all of you just had an N400 signal when I said that, or if you read that ahead of me when you read that, because that doesn't make sense to us. And so this fires when there's a pattern that we expect that doesn't come through. A couple more to go through here. So visually evoked potentials are when you're measuring from this area of the brain, which does our visual processing, if you remember back to neuroanatomy. When you're looking at a screen, you can have objects that are flickering at different speeds, so at different frequencies. And then whichever frequency you're focusing on, so if you're focusing on something that's flashing at 9 hertz, 9 times per second, you're going to have that, you'll see a signal up here that's flashing at 9 hertz. And so you know they're focusing on that object. So yeah, so here's just a little example of that, where if you're looking over here, this is flashing at whatever frequency is associated with 4, and you see very, very clearly that there's a spike for that frequency. For this one, spike over here, and et cetera. So it's very, very easy to detect because you just kind of set a threshold like right here, and then whatever goes above that, you know that they are looking at that button. So this one's kind of in the middle because you're consciously looking at things, but you can't control the response that your brain is having. And finally, here's just a little animation that I made to kind of show you that. So if you're looking at the left, this one's flashing at 6 hertz. It sees that, moves this little car to the left. And then if you're looking at this one, that 9 hertz signal is shown in the back of your brain, and then it moves the little car that way. So finally, the filtering and processing part of this. I am not by any means a machine learning expert, and this is my weaker point. So if Bryce or anybody from that team were here, I'm sure that they would be able to provide some more insight than I can. But the reason why this is important is that data is really, really messy, and you have to be able to clean that up before you can do anything from it. So those signals that we just talked about with the P300s and all the ERPs, SSVPs, those have to come after you've removed all of this noise, and that's when you find that. So an example of noise here in EEG is this is an eye blink. You can see we have brain data, brain data, brain data, and then this massive change right there, which is muscle activation from an eye blink. And so what you can do with filtering is you can look for things that break a certain threshold or that are really abnormal and remove that. And then you still have brain data there because there are little blips that go along with, that are counter to what that large jump is. And so if you do enough training to know what that looks like, you're able to pull that out and still preserve some of the data. So this here is something called a fast Fourier transform. It's really not that important to go into the technical nature of what all of it means, but basically you can take apart one signal like this that's messy and pull all of these smaller sine waves out of it so that you can kind of, if you wanted to say, I don't want to focus on these big signals, I want to focus on the smaller ones, it's a way to kind of filter through that. I was actually hoping that Bryce was here to help me explain what all of these are, but if you're interested in any brainwave processing, these are primarily what's used in filtering. So you have independent components analysis, which is similar, I believe, to what I was just talking about in terms of pulling out individual features. Principal components analysis is kind of similar to that, except now you're looking at only the features that are important to you. So those could be, like, again, if you wanted to filter out some of these big signals, you could just ignore that and focus on some of the smaller ones. And then neighborhood components is just sort of forcing things into bins. So say, these look similar, we'll put them over there. These look similar, put them over there. How am I doing, Alex? Is that close enough? All right, good. All right, so that's enough of the more learny things that we have to go over. Let's just look at some cool GIFs, and I'll just kind of tell you what's going on. If you have any questions, feel free to shout them out as we go through. So how can we actually apply all of these methods? Darn, no GIFs yet. Where's the first GIF? Okay, we got a little video. Cool. So one of the first things that you can do is visual neuroprosthetics. So you can take in, so there are 3 points where if you wanted to make a visual neuroprosthetic, so for somebody that's blind, you can put images into their brain. There are 3 areas you could do that. You could do it on the eye, in the thalamus, or on the back of the brain. And so these are just showing all different ways that you can do this, where you could put a little electrode grid on the retina and stimulate that, or kind of in the back here, and you can actually project low resolution images into the brain that way. Here's just kind of an example of what that might look like. So it might be hard for you to see, but there's a little letter E on this grid here. And so they would see a very, very low resolution image of that. It would be black and white because that's where we are right now, but theoretically you can keep scaling this and give someone vision or stimulate the back of their brain to add elements to their vision. So if you want to do some sort of AR thing where you're adding things into your normal experience, you could do that. The science supports that. We're just a little bit of a ways out from there. So hopefully this will let me skip around. Let's just do it this way. Awesome. We got an ad. How long is this ad? Cool. All right, that's a minute ad, so I'm just going to look at this image and just tell you what's in it. So this was just an animation of signal coming down here all the way to the visual areas. And so they just have a camera on someone's glasses, or sometimes they are now implanting them in the eye. And then that signal gets sent back here, and you just stimulate it like a little grid, like you would with pixels on a screen. And then you are able to project an image into that person's brain. We're still working on that. All right, we'll just move on then. See, look, here, I promise there are a lot of GIFs. We'll get there. So this one might be interesting for us at RIT because auditory neuroprosthetics is just another word for cochlear implants. That's the primary type that's being looked into. There are some that stimulate directly onto the brain, but these work a lot better. Is there anybody in here that has a cochlear implant? I'm just curious. All right, so nobody in this room, but if you have friends that do, this is how they work. So you have a module on the outside, which is the processor, and it's picking up the signal, and then it's going to transmit that down to an electrode array that's actually curled around into the cochlea here. And yeah, so this is just a very quick animation to show how hearing works, basically. So you have sound waves, which are mechanical waves that come in. They vibrate these oscillatory bones that pushes this hammer into the cochlea, and it vibrates a little membrane. So I'll show that again, and then we'll kind of go into the ear so you can see what that looks like. So again, this is mechanical energy that's getting translated into electrical energy on this membrane here. All right, can we go to the next one, please? There we go. So if we take the cochlea and spread it out and uncurl it, and Hannah, I know you were just looking at this stuff recently, so definitely check me. But if you take the cochlea and kind of peel it out, you have this long membrane here called the basilar membrane. And you can see on here that it's really, really nicely organized, where you have high frequencies down here, so your high-pitched sounds close to the base, and then low frequencies out here. And so this vibrates as you're listening to sounds, and it hits these little cells that are underneath it. And these are, when you hear people talk about hair cells, this is what they're talking about. And they're called hair cells because they have these little things called stereocilia, these little branches that go up. And they kind of sit under that membrane that I was just talking about. And when the membrane vibrates, it bends these little hair cells, and that lets in or closes out ions, and that creates an action potential or doesn't create an action potential. And so based on how many times it's causing the neurons it's touching to fire, then the brain is able to put together a picture of what you're actually listening to be able to hear sound. And so for hearing loss, so this is not for someone who's deaf or hard of hearing, there are a lot of reasons that could be. So you could have damage to these, but more likely it's damage to the nerve that's going into the brain. But for hearing loss, like going to a rock concert, if you have this basilar membrane like moving very, very quickly, it can slam down on these stereocilia and cause them to bend over and sit down. And they can take some of that. So you know how like it's hard to hear the night of, but then the next day you get up and you can hear a little bit better. So they can still kind of bounce back a little bit. But once that happens too much, they start to stay over, and then they die permanently because you just have ions flowing in that ends up killing it. You've also, if you have an iPhone, how many of you have gotten that little signal that it said, like, you've been listening to music too loud this week? Like, pretty much everybody, right? I get it consistently every week. And the sound might not be too loud in the moment, but you can actually kill the neurons downstream if you stimulate them right here too much. So if it's consistently stimulating them close to their threshold, you can also kill them from overstimulation. So then you just have this electrode array here. This is back to the cochlear implant that kind of comes in, and it curls around the cochlea. There are usually 22 electrodes on here that stimulate, and instead of mechanically opening and closing the stereocilia, it has the same effect through electrical stimulation. And so because the basilar membrane is nicely laid out, tonotopically is what we call it, but very nicely from high frequency to low frequency, you can stimulate sound pretty well. And these are the most effective neuroprosthetics and most widely used that we have. There are also tactile neuroprosthetics. So this gives you a sense of touch or a sense of pain or proprioception where your body is in space. And there are a lot of different ways that we can use these. So you have some that don't look that comfy, that are these, it's again a spike array like we saw before, but this one's on a slant. So you could implant those either up in the brain and just stimulate the areas that feel touch, or anywhere along these neurons coming down the body. So there are some that go directly into nerves, some that go into the spinal cord, some that go into muscles. So you can kind of put these at many different sites, but it's very, very cool that we can give an artificial sense of touch. And so this is the first time that that was done back in, I believe it was 2014. This is a guy, Nathan Copeland. I got to speak with him on Zoom a couple weeks ago, which is really cool. He was trying to describe what it was like to actually feel that sensation. He also got to fist bump and shake hands with President Obama, which is kind of cool, using this device. So he's able to control this using 2 implants in his motor cortex, and he has 2 more in his somatosensory cortex, and that gives him a sensation of touch. This was the first experiment that he did, and he correctly identified 19 out of the 20 touches from the experimenter, where the experimenter was just touching one of these 4 fingers. And so 19 out of 20 times he got that correct on his first try, which is really cool because it shows it doesn't require training. It just pipes itself into the circuitry that's already there. Now we have motor neuroprosthetics, which if you're on the prosthetics team, this is kind of where that integrates in. And so you can see here we have, it's a little bit blurry, but this guy is in an exosuit here. And this is for the Brazil World Cup. And they had him just think about, using motor imagery, think about kicking his leg. And when the brain-computer interface recognized that, it actually kicked out the leg of the exoskeleton. And this was like right before the start of the Brazilian World Cup, which was a really great promotional thing for neurotech. So this is, can anybody guess what technology this is using based on what we talked about before? Yeah, go for it, John. Yeah. Yep, so if you remember back when I was talking about the synchronous BCIs, I was saying that you can pick up frequencies on the back of the brain. So that's all that they're doing here. This is non-invasive interface. These are all flashing at different frequencies based on which one she's looking at. They can type. This is using that population coding, so that invasive, the thing I was trying to draw over here, looking at what preferences neurons have. And so you can see that he's able to actually control this prosthetic. How long do you think you're there, Hannah, to this point? What do you couple weeks? Yeah, great, fantastic. This is a cool program. This is the DARPA Luke arm, like for Luke Skywalker. This was about $3 million to produce that, which is kind of crazy, but this is early generation. This is another brain-controlled neuroprosthetic arm. This is all coming from brain signals you can see up on her head over here when it pans back out. And she's able to control that sort of as if it's her own arm. Of course, it's not nearly as accurate yet, but it's really cool to see what is able to be done. And then this also happened last year, or maybe December of 2020. Time is really flying away. But in December of 2020, we'll say, this person was able to use 2 neuroprosthetic arms at the same time using 6 implants, was able to feel through them, and able to cut a slice of bread using a fork and a knife and then actually feed it to himself, which is just an insane amount of dexterity to be able to have just through a brain-controlled interface. Here's one more example of an exosuit, so you can see it a little bit better. Again, this is motor imagery, so he's imagining himself moving forward. He's imagining picking up his leg and then picking up his other one. And you can see that he's actually able to drive the system and turn it and move it around. It's pretty slow, but very, very cool first steps there. This one is also using, does anybody want to guess what technology this one is? You can go for it again, sure. So this would be population coding. So you don't need, so it doesn't have to be one jump like that, but if you imagine kind of your arm just pointing this, that's essentially what they're doing, and they're using population coding to, she's moving a mouse around on a screen and able to type with that. So for gaming, this isn't really a neuroprosthetic, but it's growing really, really quickly and kind of interesting, so I thought I would mention it. This is from our friends over at OpenBCI. All the hardware that we use, for better or for worse, is from OpenBCI. So you can see they've got their little VR headset there, and then I'm assuming they'll use SSVEP because of the location of these, and maybe some ERPs as well, because we've got some up on the top, to integrate into a gaming experience. And I'm really, really excited to see what they come up with, because they've been teasing this for a while, and they collaborated with Oculus and Steam for this headset. And so this should be coming out sometime later this year. This was from a company called Control Labs that was bought by Facebook for $50 million in 2019. And you can see this is just using EMG. There's a little bracelet on his hand. And just by reading out those muscle signals, he's able to get a really accurate representation of that hand, down to the point where you can touch type on a desk, and it's able to pretty accurately detect which keys you want to hit. So this is really cool for like a VR application where you could theoretically have perfect hand mapping in a VR environment. Okay, so here we've got, again, Elon Musk's company Neuralink. You may have seen this filtering around through the internet, but this is the first demonstration that they had of their device where he's playing Pong. You can see he's a little bit preoccupied by the grape juice that he's getting. For every successful hit that he gets, there's a little bit of grape juice, but he's actually pretty good. And Nathan Copeland, the guy that I showed before, publicly challenged Elon Musk and him and the monkey on Twitter to a Pong battle using brain-computer interfaces. And so hopefully that will happen at some point. I'm crossing my fingers. I think that would be really funny. But my money's on the monkey because he's doing pretty well. So this is just using focus. This is really easy to do. You can just use the BCI's focus widget to control a drone just to make it go up and down. Theoretically, you could use something like SSVEP to make it go forward, back, left, or right as well if you're interested in that. And then this is motor imagery again. So imagining yourself moving forward to the left or to the right, and fairly well, he's able to control this just by imagining that movement. I don't know what game that is or if it's a game that they made specifically for this, but you can see it's pretty interesting and it's working well. All right, another video. Hopefully we won't have an ad, but this is from Nathan Copeland's YouTube channel. So he just has this device at home. He'll play video games. He's been painting NFTs. And so this is an example of him using his brain-computer interface to play that. And so if you're interested, you can look at BCI Can Do Better is his handle. And he has lots of videos of him playing various games. I think he played is it League of Legends or something too? He's played a bunch of different games. But you can see he's able to do reasonably well moving that guy around. And of course, this is all just controlled with his brain, which is kind of wild. It's honestly better than I can do, so I'm very impressed. We'll see. Let's see if we can find some more here. Hopefully we won't be dealing with ads. Oh, we have a lot of stuff in the chat. Oh, good. Alex, you're on that?
Yeah.
Thank you. And John, yeah. So let's see what we have. So this one, he has been getting it another minute ad. Jesus. Hold on, let's go back. It's just, yeah, seriously. Did that just open? Okay, cool. So we'll let that load. Maybe this one will work. Maybe not, we'll see. But he played Final Fantasy. Yeah, there we go. So he has just started streaming on Twitch. And so if you're interested in watching a BCI gamer, you can see his invasive implant right on the back there. Where's his head? Yeah, up there. And he's able to move the character around, select different items, and attack. And so it's kind of fun watching him do that. Again, if you find him, you can see his Twitch streams. And then here's him painting an NFT. It's the first NFT to be created by a brain-computer interface. So kind of hard to see, but You can see his cursor is moving around on this screen. He's got some Spotify up over here. He's got quite a setup, honestly, with these four monitors, it looks like. But he's able to do all of that just by thinking about it, thinking about what direction he wants to move that in. How many more do we have? OK, that was it. So this is the last one. Again, for candy if you want it, and you can all have candy, but for more candy, I guess, can anybody guess what technology this is using underlying? I'm not giving it to you yet. Does anybody else have a guess? Close. It is the SSVP stuff.
So they're all fucking lollipop at me right there.
OK.
Make sure to chuck it. No, please don't. It's gonna be on one. It's gonna kill me.
I'll throw it off to the side. There you go. Yes. So this is P300 was a good guess, but this is SSVP. Or no, actually, hold on. Yeah. So I just kind of put some GIFs in there. Now I'm thinking about it because they are.
I don't know.
Yeah, I'm pretty sure it's Yeah, it is SSVP because, so see, that was a good answer because I was confused for a little bit there. It's SSVP because I think it's probably hard to see in this, but they are flashing at different rates, and the pickup is from the back of the head there. But depending on, you could do this using P300 if the flashing rate was the same. And if you're measuring from up on top of the head, it would look quite similar to that. So honestly, either one of those were good answers. And just when that lights up, you would see that. All right, I'm going to end it there. I was going to explain the vestibular system as well for vestibular neuroprosthetics, but that's a whole nother thing, and I don't want to bore you guys with that. But basically, there are ways for people with vertigo or people that lose their vestibular senses. It is quite dysregulating, and they're working on making neuroprosthetics that can help with that too, just by stimulating within these areas. Afterwards, after I let everybody go, if you're interested in that, I can stick around, but we will go ahead and call it there. So come get some candy.